Alright, did you see a pattern? If our slope is a fraction, and the fraction is in reduced form, meaning that the top and the bottom, or the numerator and the denominator, don't have any common factors, what happens? The numerator is the number of times we go out the top, and the denominator is the number of times we go out the side before we get right back to where we started.
So you basically take the denominators and then you put the one that's at the top on the top and the one that's on the bottom on the bottom.
Yep. If we have 2, we go out once, then back. If we had a half, go out once, and then back. Kind of crazy, huh? Now, of course, this doesn't work if our slope is not in reduced form. For instance, if we had 4 over 2, that would be the same as 2 over 1, right? And of course, either way, the slope is 2, and it's only going to go out twice. Let's pause for a moment and see what it means for our line to come back to this bottom left corner. On the whole plane, that means that our line at some point hits an integer point. All the integer points on the plane, kind of the intersection points of our grid, correspond to that bottom left corner.
Is it possible to draw a line here on this picture that never hits one of these grid points? Because if it never hit one of those grid points, we'd never hit there and we'd never get back to here, right?
Like
Never hit one of those grid points.
Yes. No. You go like this. No.
What would it mean? What would it mean about the slope if we did that?
That it's not.
Wouldn't be undefined, right? Because it's it's got a slope. We could go and look at it. We could take a measurement of how far across we've gone and then how far up. It doesn't make any sense. You know what? The Greeks said that this didn't make sense. The Greeks were so upset about this, and by Greeks I mean the ancient Greeks, not the modern day Greeks, because the modern day Greeks understand this as well. The ancient Greeks were so upset about the idea that you might be able to do a line like this that they put someone to death for suggesting that it was possible. The ancient Greeks took their mathematics a little bit too seriously.
In fact, the Greeks thought all numbers should be able to be expressed as a ratio of 2 numbers, and any numbers that they couldn't, well, they just didn't believe they existed. I have a little confession to make. That slider that you had that allowed you to choose the different slopes, I only let you choose fractions, but there are other numbers. There's actually lots of other numbers. In fact, we'll go and have a look at that in another exploration, one where we talk about infinity. For now though, just know that there are numbers like square root of 2, pi, some of you might have heard of e. These numbers are all irrational. Now that doesn't mean that those numbers are crazy. That just means you can't express them as a ratio of one whole number divided by another whole number. But if we're at irrational slope, that means we never repeat. Because repeating would mean getting back to that bottom corner. That would mean landing somewhere on a grid point. So irrational slope, meaning a slope that's not a fraction, means that we never come back to that bottom corner in our little video game square. That's crazy, huh? So wait a minute, if we never come back to that bottom, that means that every time I draw another line on this piece of paper, it's somewhere that we weren't before. And if it's somewhere we weren't before, and we keep drawing more and more of them, drawing more and more lines, and none of the lines ever touch points that they touched before, what's it going to end up looking like?
But it's never going to hit this point here again, and it's actually never going to hit any of the other points again, but it'll start getting it's called denser and denser.
Kind of looks like we're going to fill up that whole square. But here's a question for you. Will we fill up that whole square? I want you to have a play with this. The next little interactive allows you to pick slopes that are only irrational. And what I want you to try and do is see if you can use one of those irrational slopes to hit a rational point. That is a point that's got coordinates made up of fractional coordinates. Go on, have a shot, see how you go.